then perfect. So now we are ready to proceed with our second talk of the day. And the talk will be given by Federico Olimpieri, and the title is going to be Categorifying Intersection Types. Federico, you can start whenever you want.
Yeah, thank you. Yeah, I'd like to first thank the organizers for inviting me to give this talk to Ithaca. The topic of the talk is going to be quite different from the one by Domenico, and it's actually about applied category theory to semantics of programming languages, in particular to the semantics of lambda calculus. So I will start by an introduction. So I will give some, I won't assume much about knowledge on functional programming languages in lambda calculus, because we are going to talk about semantics of this kind of things, and I'm going to give some intuition introduction on this. Then I will talk about some kind of typing system for these programs, so for the lambda terms that are strictly related to a particular categorical structure, the category of sets and relations. Then I will categorify all this in the setting of distributors and present the corresponding semantics for lambda calculus that I call intersection type distributors. Distributors are profunctors, okay? So let's start. The topic is going to be at the intersection, okay, of three domains that are logic, programming language theory, in particular the semantics of programming languages, functional programming languages, and category theory. Okay, in the classic shape of the point of view is going to be the classic correspondence, carry-over lambda correspondence between the intuitionistic logic, the simply type lambda calculus, and Cartesian closed categories. So first, what is the notion of programs that I'm talking about? Is the functional one. So the idea is that I'm going to be very naive point of view. It's just the idea that you can see a program, if you forget about side effects, as something that takes an input and returns an output. So some kind of function. For instance, you can get a program for multiplication that you can see as a function that takes two integers and return the product of the two. Okay. And this function clearly is performing a procedure, okay? So it's following some kind of instructions. And in particular, you want that your function behaves in an appropriate way. And so you are normally, you give specification of these programs. You are seeing them as a function. So in particular, this multiplication function will be something that starts from a type that is the product type between not integers, okay, positive integers, and returns an integer, okay. So this is an arrow type, and it's actually the same as via carrying. So you can already see quite an important categorical structure hidden there. That is the Cartesian closed structure. This is the same as a function that first takes an integer and then returns another function that takes an integer and gives the multiplication as output. So the formalization of this kind of idea, the standard one, is the lambda calculus. That is a very simple language. So I'm starting to give some syntax. This is going to be quite, we're going to have quite some syntactic definition in this talk, actually. And so the definition is an inductive one, quite simple, very minimal language. You have, you fix an infinite countable set of variable, okay, x, so a lambda term is either a variable, either this syntactic construction that is called a lambda abstraction, so you take a variable and you, m is a lambda term, and so you get lambda xm is a lambda term, and then you get what is called the functional application, where m, you are applying a term m to m, and this is already, again, another lambda term. The intuition behind that is indeed that the lambda abstraction generates functions. In particular, it's the function that to x is going to associate m, and m applied to n is indeed a function application. And lambda calculus is a programming language in the sense that you have a very simple evaluation procedure that is given by what is called the beta reduction. And it's just when you have this construction that is a function lambda xm applied to an argument n, this is reduces, okay, by a step. This is a relation, okay, between lambda terms, and reduces to a term where we are substituting all the occurrences of x in the body of m by n. So this is the basic step of computation for lambda calculus. Some easy examples are, for instance, the identity function applied to your favorite lambda term is going to beta reduce to the lambda term, to the input. For this reason, is the identity. We are going to replace the only one occurrence of x. Okay, and also you have a way to encode our multiplication function. You can encode also integers. In particular, lambda calculus is equivalent to Turing machines as a model of computation. It's Turing complete. You can perform all the computation that you want, and this is going to reduce, okay, in 3 steps if you want to your result of multiplication. So you are performing substitution at each step. Now we have what we are talking about, so lambda calculus, but I'm going to talk about also logic, in particular what is minimal logic, so a very simple structure. And in general, in logic, you get again syntactic construction that gives you the formula of your logic. Then you can build by rules the 3 derivations that are proofs in your logic, and then you have a procedure called cat elimination that is actually quite important. And for instance, we are talking about intuitionistic minimal logic, so we are actually just consider implication. Okay, this is the implication. Gamma is just a set of assumptions under which you are proving formulas, and this symbol means that from the assumption gamma and A you can derive B. Okay, P1 is a derivation, P2 is another derivation. Then you get this introduction of the implication that is quite a straightforward rule, and then an elimination of implication that is what is called also modus ponens. This construction is called cat, actually, and you can transform it, your general derivation, to one where this kind of construction disappear, and they have a very natural interpretation via lambda calculus, because actually you can associate to each derivation in this very simple system a lambda term that is called the simply typed lambda calculus. And in particular, now this kind of procedure of eliminating these cats, okay, this structure of first you do introduction, then elimination, is actually the beta reduction. So it's actually the evaluation step of your programming languages. So this system, this very simple system of logic, corresponds to a particular class of programs that are called the simply typed lambda calculus. So types are formula now. Clearly, lambda xm is a function. Indeed, it's going to have an arrow type that is going to be the same as the implication of our logic. And then evaluation is this kind of procedure that is called cat elimination. And then you have also the categorical point of view that was introduced by Lambek, but already was somehow present in some lower papers in the 60s. And now formula are going to be interpreted by objects of your category. Then programs and proofs are going to become morphisms between these objects, between these types. And then the evaluation procedure is actually preserved up to a quality of this kind of interpretation. In particular, this is called the denotational semantics. It was introduced first by Streich and Scott in the 70s. And it means that if your term M reduces to N, then in particular, the denotation of M, okay, the morphism in the category is going to be the same. So it's the interpretation is sound up to the reduction of your terms, so up to computation. Now I'm going to be a bit more specific about how you give this categorical interpretation, so the categorical side of all this. And it's very simple. So we started from a simple logic where you just have an implication and O is an atom type, okay? So you just get another, just a function that to atoms gives objects of your category, Cartesian closed in particular category. Since to give the interpretation of the arrow type, you need an exponential object. So the interpretation of the arrow type is going to be indeed the exponential object. And then context of assumptions, 3 variables for your term, is going to be given by just taking the product of this interpretation of the formula. In particular, lambda term, typed lambda term, is going to be seen as morphism between the interpretation of his context to the interpretation of his type. It is lambda calculus indeed called the internal language of a Cartesian closed category for this reason. Okay? And the interpretation completely exploits the Cartesian closed structure. For instance, the interpretation of a variable is going to be a projection. Okay, the interpretation of a lambda structure, so a function, is going to be clearly given by the carrying operation of your Cartesian closed structure, while the interpretation of a functional application depends on a pairing and then post-composition with the evaluation morphism, again given both of them by the Cartesian closed structure. So in this sense, lambda terms can be seen as morphisms in your Cartesian closed category. Now we have this picture, this nice picture that is a classic one between intuitionistic logic, simply type lambda calculus, and Cartesian closed categories. But actually, you can refine this point of view because Girard in the 80s discovered that the intuitionistic implication, so the linear, the arrow type for lambda terms, if you want also the exponential object of your Cartesian closed category, can be decomposed in more essential constructors. This new implication is called the linear implication, and this this modality is called the exponential modality. Okay, the exclamation point is called the exponential modality of bang operation. And in particular, now, this decomposition gives you the possibility to distinguish between linear and nonlinear computational behavior of programs. In particular, you have that a linear program is going to be a program that uses its input only once during the computation, while a nonlinear program could use it more than once or actually 0 times. Okay, for instance, the identity function is linear, since it's going to use m just once, while the multiplication, okay, this kind of multiplication is actually nonlinear, so it's going to copy your input, okay, 2 times. So it breaks linearity, and indeed its type is going to use the bang operation, because the bang, this exponential modality breaks this kind of linear intuition that is about how many times you are using the input during computation. It turns out that this kind of decomposition can be seen in a very nice way from a categorical point of view. That is, you actually see the linear implication as a right adjoint to a tensor product. So you start from a symmetric monoidal closed category. Okay, so this new arrow is a right adjoint to a tensor product, not to a Cartesian product. Then if you add also finite products and a comonad that is going to give the interpretation of this modality. So this modality that breaks linearity is given by a comonad construction. You take the Kleisli category of your Cartesian of this comonad, and this is going to be Cartesian closed. Actually, you have also to impose some monoidality on this endofunctor, the endofunctor of the comonad, for this to work. But still, this is an important theorem, and means that you can actually build Cartesian closed categories starting from a more primitive stuff that has a very strong, relevant computational and logical meaning, because a symmetric monoidal closed category is going to be a model of linear programs, if you want. And then the comonad gives you the possibility to have non-linear programs. Now, this is the general categorical framework. It's now it's more or less well known in the domain, and in particular, I'm going to focus on some special case of interpretation for lambda calculus given by this idea of linear logic decomposition in the category of sets and relations. But first, I will go back to some syntax, so syntactic point of view, about what are called the intersection types. So we have the simple types that were just the atoms and the implication, okay, A or B. Intersection types were first introduced by Coppe Design in the late 70s as an extension of this simple typing, where you had this syntactic constructor called the intersection type A intersection B, then an empty intersection omega. The idea is quite simple, okay, and it is that you can, a program that is both typable with type A and B should be typable with intersection type A intersection B in particular, and all program is going to be typable with the empty intersection omega. Now, the intersection, you can impose associativity, commutativity, and potency over it, okay, if you want. Generally, it's very important to have associativity, okay, and also commutativity, but idempotency can be relaxed. And indeed, if you don't impose idempotency, your system is resource sensitive in the sense that the typing of the term is going to give you the exact number of times that the term uses its input during computation. So a very resource sensitive point of view that clearly is somehow related to linear logic. We are going to see how from also a categorical point of view. And this kind of system are very useful in the lambda calculus. Okay, you can characterize important notions that are called the normalization notions. That means you can characterize classes of programs for which computation ends. Okay, so you can characterize termination, different notion of the termination, and also talking about some complexity issue, like execution time of programs. But the important thing for our talk is that this kind of timing system gives a very simple denotational semantics, so something that actually is preserved under reduction, under evaluation, just takes the context and the types under which your term is typable in this system, and this is preserved under reduction. And how this actually relates to category theory and categorical semantics in particular, the context that we have to consider is the one of the relational model. So we are in the category of sets and relations. Objects are just sets, and morphisms are relations between these sets, so a very simple structure. And here we say that actually we want a model for programming for lambda calculus. So we need a Cartesian closed category where we will pass through this idea of linear logic, starting from a symmetric monoidal closed category and then adding this comonoidal construction. And ReL is clearly monoidal closed. It is in a very trivial way because the tensor product is just the product of sets, and also the linear exponential. So the right adjoint to tensor product is just again the product of sets. So it's completely trivialized the distinction, if you want, but it's quite important still. And indeed, the linear arrow you take as the comonad that you are considering the free commutative monoid construction. So just the multiset construction over a set. Okay, multiset is just a list where you forget about the order, and it's indeed a way to describe the free commutative monoid construction, the underlying set of this algebraic construction. And indeed, the intuitionistic arrow, so the arrow in your Cartesian closed category, is constructed using the linear logic point of view, and is given by just Cartesian product of sets, where you are performing a multi-sets construction over A. So you take the free commutative monoid over A times B. And this kind of linear categorical semantics has a very nice syntactic presentation somehow, in the sense that an element, so we started from syntax, you go to the semantics using the relational model, and then again inside the semantics, so inside the model, you can give actually some new syntactic information you can actually achieve. And the idea is that an element of this, okay, so this set where the first are going to be pairs, where the first component is multisets, okay, of element of A, and the second one is an element of B. So these pairs, you are going to see them as a new kind of types, okay, indeed the intersection types, where the intersection construction is given by the product of your monoid, commutative monoid, okay? You are seeing the product of your commutative monoid as the intersection construction. This is just syntactic sugar for that, if you want, but it has very nice meaning from a computational point of view. And this was first remarked by Daniel de Carvalho in his thesis. And in particular, it gives rise to a non-idempotent intersection type system, where the intersection non-idempotent is given by the multiset construction, where you can characterize important notions in lambda calculus. I'm not going to get technical on that. Solvability means that you are actually typable in this system, derives from the semantics, if and only if the term is computationally meaningful. Okay, I'm not going to give the details, just this intuition of. So it's an important property of programs, and you can characterize it using the relational model via this syntactic presentation of it. In particular, we have seen that a lambda term in categorical semantics is seen as a morphism inside your Cartesian closed category. And since we are giving in syntactic presentation to this semantics, the morphism itself can be seen in a syntactic way if you want, because if you take the characteristic function point of view, M is going to be a relation, but if you see it as the characteristic function of this relation, this is some kind of test of typeability somehow, in the sense that we'll return one. It takes a context delta and a little type A that is intersection type, okay? So it's inside the semantics, and returns one if actually M is typeable under this context with type A or 0 otherwise. So you have this very nice way to see the interpretation of a term inside this category, and this has been widely studied and applied in a very lots of ways. But there is something unsatisfactory from this point of view, at least from a proof theoretic point of view, if you want, is that if you take another structure, that is, you take your term M and then intersection type context and intersection type A, and return all the type in derivation of M under this context with this type, this is clearly not a relation, okay, because it's not a characteristic function of a relation, clearly. It's not even denotational semantics in the sense that this is not preserved under reduction in general, not even up to bijection. But it's a very important structure because when you consider typing system, so also intersection type system, you actually work with typing derivation. You would like to talk about them semantically also, since we are giving this semantic idea of intersection type using relations. And so it's unsatisfactory. We would like to fix this, because otherwise we are reasoning on typing derivation outside the model, while it would be nice to have a general categorical way to think about these things, since then you could apply general categorical construction to them. And in order to do so, we are going to perform a categorification. So we are going to replace the set theoretic notion with category theoretic ones. Sets are going to be replaced with categories, functions are going to be replaced with functors, equations between sets with isomorphism between them, and the equation between function with a natural isomorphism between these functors. And in particular, in this context, relations are replaced with distributors or profunctors. This categorification process will allow us to pass from the proof-irrelevant semantics, where the relation associated to lambda term can be seen as the characteristic function that gives this test of typeability 1, 0, depending on the typeability of your term. This you can actually finally achieve a proof-relevant structure, where not only you get typeability, but actually you take a context delta and a type A, and this returns all the type in derivation of your term under the context with this type up to an appropriate congruence. And this new information is actually relevant in the computationally relevant in the study of lambda calculus. So we will achieve a categorification, okay? So we are making things explicit. In particular, we will achieve refinement and improvement of an important semantics of program, that is the relational semantics linked with this kind of intersection types. And a parametric syntactic presentation of, if you want, abstract and esoteric models, in the sense that it's a bicategorical model, so second dimension, for lambda calculus, given by Kleisli bicategories of distributors or profunctors. And this gives a very general semantic theory of this kind of typing system, intersection types, plus a notion of subtyping, okay, categorical subtyping, given by morphism, possible morphism between these types. And in particular, also a dynamic denotational semantics, because I said before that beta reduction is normally validated up to equality in standard categorical semantics, while now in this context, it's actually up to natural isomorphism. So you have some dynamic flavor. You can actually talk about rewriting evaluation of your program inside the bicategory, because now you have the two cells, and in particular, beta reduction is now a two cell. So you have a very nice way to talk about a very important thing of programs, that is the computation, okay, so the evaluation. Now, taking this in mind, we are going to go a bit more technical. Okay, the starting point, you have your category of relations. You can actually generalize it to a category of preorders and monotonic relations. Then you have a comonad over this category that gives you the exponential of linear logic. In particular, resources or intersection types are given by this multiset construction, but because you are always considering the free commutative monoid construction. So remember, the elements of the free commutative monoid are important. You have a standard notion of subtyping in the sense that if you take preorders, you get a preorder over types. And this is what type theory is called subtyping, just the fact that you have a preorder over types. And a proof-irrelevant and static semantics in the sense that I told before. It's static because it's up to equality. It's proof-irrelevant because it talks just about typeability in this kind of semantic typing systems. Now you categorify, you replace these preorders and monotonic relations with distributors, okay, so with small categories and distributors and natural transformation between them. Then the comonad becomes a pseudomonad. Actually, if you want a pseudo-comonad, but we will work with pseudomonad and then dualize actually. And then now intersection types and resources becomes lists. So we are making things explicit because the free commutative monoid construction is going to be replaced by a free strict monoidal construction, okay, over a small category. Standard subtyping becomes categorical subtyping in the sense that now you just don't have preordered, but also morphisms, different way to subtype and type, okay, different way, because you can get different morphisms in general. And finally, a proof-relevant dynamic, since we are in a two-dimensional setting. So everybody knows relations. The important thing is to keep in mind the characteristic function point of view, because we are talking about actually distributors that widely generalize this point of view. Okay, you just take small categories, and then a distributor between A and B is a function between the opposite category of B times A to the whole category of sets. So we are replacing the two elements Boolean algebra with the whole category of sets. So you're changing enrichment. And composition of relation is the standard one, while composition of distributors is given by a Cohen formula. Okay, this is more or less well known in category theory community, I think. And since we are in the set enriched setting, this just boils down to sum over these sets up to an appropriate congruence given by action of morphism in the category B. And since we are working with cohens, actually distributors are bicategory and not just a strict two category. Okay, bicategory for me is what other people call weak two category or just two category. Okay, so a bicategory consists of just a set of zero cells. Then we have okay, just the home category between two objects, where you can have also morphism between one cells that are called two cells. And then the horizontal composition is associative and unitary only up to coherent isomorphism. Okay, this is quite well known, I think, for the audience here. And this is a generalization of the notion of monoidal category, if you want, since a monoidal category is a one object bicategory. Now, distributors are bicategory in a quite natural way. It's a quite natural example of bicategory. They were introduced by Benabou. Zero cells are small categories. One cells are distributors between these small categories. And then two cells between these distributors are just natural transformations. In particular, distributors are compact closed. Okay, so you are in particular monoidal closed. Bimonoidal closed, if you want. And the tensor product is given by the product of small categories. The linear arrow is given by product of small categories again, but now it's actually not non-trivial in the sense that you also perform the dualization. You are using the orthogonal structure of the compact closed category that is given by the opposite category construction. So as you can see, this generalizes very naturally what happens in the relational case, but it's less trivial. And then the Cartesian product that I write like this, the commercial end, because it's the linear logic notation, is given by this joint union of small categories. And for distributors were first considered in the context of categorical semantics by Cattani and Winsker. Now we have our compact closed categories, in particular our monoidal closed category, and we want still exponential construction, because we are looking for a model of lambda calculus, not just linear programs for the whole lambda calculus. And for this, we need the comonad, okay? The comonad construction that normally in linear logic, okay, is given, for instance, in the relational standard relational case, we already talked about that. It's just the free commutative monad construction. They are the line set of this construction. And you can completely generalize this to the case where you switch from sets and relations to preorders and monotonic relations. In the case of preorders and monotonic relation, you can get also an idempotent notion of intersection type, because now you take the underlying preorder of the free bounded mid semilattice, and this is the preorder gives you idempotency, okay, because you are taking a mid semilattice. And okay, and the fact to switch from monad to the other one gives you different notion of intersection types. So the main idea is that intersection types are given by the notion of monad that you are choosing, and you can get different one, taking different monads at the beginning. We want to do this for distributors, so we start from small categories, 2 monads over small categories. Idea again is they are going to talk about intersection types and particular resource management, because intersection types talk about how you are actually using the input. Okay, there are bags of times that you are using your input in your program, if you want. And this kind of monad, 2 monads, takes a small category and return a free S strict monoidal category. S means that it has some additional property depending on the monad that we are considering. In particular, we will consider 4 different resource monads, I call them like that. And the linear one, where your tensor product is going to be symmetric, but without terminal object and diagonals, so just symmetric tensor product. While the semi-Cartesian or affine one, you can also have the fact that the unit is the terminal object. Okay, you have symmetry, but also the unit as terminal object. In the relevant one, you don't have terminal objects, but you have diagonals for your tensor product. And the Cartesian one, you have the tensor product is actually a Cartesian product, so you have everything. There is a very nice parametric compact definition of this kind of free construction that is given as follows. So the elements of this SA, the free monoidal construction of array, are always lists of element of A. Okay, and the morphisms between these lists are given by list of morphisms, where you have this function, indexing function. The type of this function gives you the different monads. For instance, if this function are restricted to the bijections, you get the linear monad, while if this function are restricted to injection, you get the affine monad, so the semi-Cartesian one. And if they are restricted to rejection, you get the relevant one. And if they are general function, you get Cartesian monad. Okay. So it's a very nice compact definition, and particularly suitable for our computational intuition behind it, because indeed the idea is as follows. For instance, in the linear case, you get lists of intersection types that you have to think about them as a way to arrange resources. And in the linear case, you can switch, okay? You can eventually perform permutation and then use also morphisms. That gives you a notion of subtyping. This was the idea. Then in the same Cartesian case, you can actually delete these resources, okay, because you have that the unit is a terminal object. In particular, the unit is the empty list. And from the computational interpretation, okay, point of view, this means that you can delete resources. In this case, in the relevant case, you can actually duplicate resources. Again, you can perform permutation and copying operation. And in the Cartesian case, you can do everything. So you can delete, you can copy, and you can shift. So we are passing from notion of intersection types where you actually impose associative commutative idempotency. In this case, actually, you have possible operation over lists. So this strict equality becomes now eventual isomorphism or morphism between lists. We have now this collection of monads over distributors, two monads over categories. We want to lift them to distributors. How can we lift these monads to distributors? We follow a general method introduced by Fiore, Gambino, Island, and Winskill using the notion of relative pseudomonad. Okay, there is a corresponding notion of classic bicategory for relative pseudomonads. I'm not going to give technical details. In particular, you get parametric classically bicategory, parametric over the true monad that you are choosing over small categories, the S, okay, the S resource monad. Then you take the opposite by category, okay, where you actually make inversion of one cells but not two cells. And I call this category the S-Categorical Symmetric Sequences category. It's from some intuition by a work of Gambino and Joyal. But it's actually a very, it's a parametric generalization of the Cartesian, of the bicategory of generalized species of structure. So for those of you who knows a bit about species of structures, so about Joyal work on combinatorial species, the generalized species are actually our construction in the case that S is the linear resource monad, and give a categorification of the standard notion of species of structure. Our work is about a parametric generalization of this, but from a point of view of this intersection type interpretation. But there is this okay, underlining combinatorial, strong combinatorial flavor to all this. And there is a theorem: if the tensor product over the free construction is symmetric, then this is in particular Cartesian closed. All the two monads that I presented actually have satisfy this. You could also think to consider the free construction where the tensor product is not symmetric. In that case, you don't get Cartesian closeness, so you don't get a semantics of lambda calculus in particular. And now we have our Cartesian closed construction that is parametric over this collection of two monads over small categories. I want to give you an intuition about how this can be actually seen in a syntactic way using this idea of intersection types. Already I talked about a little bit about that when I presented the monadic construction. Okay.
Federico, just to inform you, you have 5 to 7 minutes.
Okay, thank you. So we have a model of simply type lambda calculus. We can actually do untyped lambda calculus. So all you can give interpretation to all lambda terms, not just the one that I typed in with intuitionistic logic. To do that, you actually define what is a reflexive object in your category. In our case, we are working with bicategories, so you have to relax a bit the notion that is okay, the corresponding notion of reflexive object. In particular, this means that you have a retraction between the exponential object of D to D itself. And how can we build this? There is a general construction. Okay, just fix a small category, then you define by induction family, a small category. And you take the colimit of this family. Okay, this is actually just the standard construction of free algebra for an unpointed endofactor that goes back at, I think, to Kelly. I think it's Kelly that first explicitly defined this. And you use it to get your reflexive object, because this colimit, that is the free algebra, being the free algebra, immediately gives you the fact that you get a retraction. So this construction is performed on small categories, but then you can lift this to distributors and satisfies the retraction condition. But the interesting thing from our point of view is that this colimit construction can be explicitly defined as a category of intersection types, where you start from atoms type that are given by the object of your small category A, then you build intersection type via the list construction that is given by the monad. And the arrow type is just syntactic sugar for pairing. And then you get morphism that are the atomic morphism given in the small category that you are considering. You get morphism between arrows that are controvariant on the list side, okay, because remember that these are morphisms between these pairs, and the first component is always a list, and it is contravariant because the arrow, the intuitionistic arrow, is given by the op and times construction. And then you have morphism between lists that is just the construction that you get by the monad. Okay, and this is what I call categorical subtyping, the morphism defined like this in this category of types. And in particular, from this category of types, you can build a typing system. Okay, this is quite sympathetic. I don't want you to get in the details, just to give a bit of, okay, to see what the typing system look like. And you have 3 rules, because you have 3 kind of terms. That is variable, the abstraction, and the application. You get corresponding rules, okay, that you're building from the model. Actually, you are looking at the interpretation of the term, and you can extract from it this syntactic presentation. In the left side, there is the standard relational construction. On the right side, there is the categorification. As you see, in the categorification, you replace the pre-order with this categorical notion of subtyping, that is the morphism between types given in the reflexive object. So in that retraction that gives the category of types. And now you have typing derivation, you have intersection types. You can actually define, using morphism between intersection types and morphism between contexts of intersection type that are just tuples. Okay, eta is a morphism of tuples. You can actually define an action, left and right action on typing derivation. Okay, that it always boils down to doing post and precomposition over this morphism that you are choosing at the level of the variable. And in particular, this notion of action gives you the possibility to define a distributor that I call the S intersection type distributor, because it depends on the 2 monad S. Actually, it depends also on the small category that you are considering, so 2 parameters. And this intersection type distributor takes, it's the interpretation of M. The idea is like that. And indeed, it will take intersection type context, the typing that you are giving to the free variable of your term, and intersection type A will return all the typing derivation of M under this context with this type, up to a congruence. The congruence is given by the composition of distributors. Okay, and finally, this is actually the proof-relevant structure that you wanted. We proved, it's actually my leaks paper of 2021, that the interpretation in this parametric bicategory is a natural isomorphic to this intersection type construction that is again parametric. So this is in a very strong sense syntactic presentation of the semantics of a term in this bicategorical construction. You get your dynamic denotational semantics. Okay. And finally, you can generalize nice results over the standard relational models to this context. This is about header normalization, is a notion of termination for computation. Okay, it's an important notion in lambda calculus. You can characterize it if actually the interpretation of your term is different from the empty distributor, then your term actually is computationally meaningful. This is the if and only if. Okay. So we achieved categorification of a relevant class of intersection type systems and an important notion of categorical semantics for lambda calculus, that is the relational semantics. We also have this extended to other notions of functional programming that is called, for instance, the Kolbe-Push value, but okay, this is just computer science things. Then this kind of interpretation can actually have the meaning of approximation of the behavior of a lambda term. So one of these intersection type and derivation that are given by the distributors that model your term in the bicategory can be seen as approximation of the general behavior of your term. I did this in my PhD thesis. And there is an ongoing work to study what happens actually with spans. So we have something about distributors, we know that distributor and spans are quite connected, but actually they are not the same thing. And there's something interesting going on, like we are working on a semantics given by Polandra Méliès about this. And for instance, it seems that the reduction of lambda terms is now preserved up to homotopy, in the sense that up to equivalence of categories. And then I'm also studying the equational theories generated by this model. What means for two terms to have the same interpretation of these models? What are the characterization of this? I'm actually looking at that. So thank you. This is all that I wanted to say.
Okay, thank you very much, Federico, for the nice presentation. And now we move to question time. So after, of course, we thank the speaker with our round of silent applause. We move to question time. So if someone wants to ask a question, please unmute your mic and ask. So while people choose whether they have questions, I wanted to ask you, Federico. So this was all very nice, but do you have some directions where you want to bring this, or you consider this a completed project?
Yeah. So it's not yet completed, I'd say, because we already have some nice results that generalize what happens already in the dimensional case for the semantics. But yeah, for instance, I'm working on this relationship between what happens in the interpretation of spans and the interpretation of distributors, that I think it's quite an open question still. And also I'd like to see what kind of more concrete results one could get using this very strong categorical construction, like for instance some result about the complexity about reduction of these terms. Really something that can be of quite of interest about for new results that can be of interest from computer science point of view. For now, this at least is my goal, if I can get something like that.
Thank you.
Actually, I have a couple of questions, if I can.
Of course, Francesco.
So the first one is if you can say something about the relationship of your work with the one by Méliès about functors as type refinement systems, which because it looks quite similar in some sense and also different from another point of view. But so can you elaborate a bit on this?
Yes, I can. Actually, this is a quite very good question, because that point of view was elaborated further by Mazza, Pellissier, and Vial, and indeed they do something very closely related to what I did, but the relationship between the two is not completely straightforward. I think that this, my point of view, that was a quite standard semantic point of view, can be rephrased in that context using the notion of operads, actually, because you can see this type in derivation in an operatic way, because actually you use the standard result that you can encode operads in distributors, and indeed this type in derivation are going to be seen as corollas, if you want. And this point of view was already exploited a bit by Mazza, Pellissier, and Vial, but they don't get actually this. It's not an equivalent construction. I think that you can go in that direction and write this down in the same way, like getting something like the Méliès approach, to where you actually consider lambda terms in an operatic way. So it's a more general approach, and also by dimension. You also need the second dimension somehow, because you need to talk about reduction. But for now, it's speculative. I actually don't know how technically this could work out, but yeah, I think that you can rephrase it like that, and it would be interesting. I mean, yeah.
So thanks. Can I ask another question? Or
Yeah.
Yes, you can.
So and what about computational effects? So there are some work in from an operational point of view that use intersection types to establish properties of lambda calculus with computational effect. I have in mind in particular an intersection type system for probabilistic lambda calculus by Dal Lago, Faggiana, and Ronchi della Rocca, I guess, at POPL 2021. So does this, your work extends also to monads in sense?
Yeah, this is another very good question, because I think yes, since my work actually generalized something done by Tsukada Sadeong. They did it just in a particular case of this general construction, and they managed to get something about probabilistic computation. So I would say that yes, you should be able to extend this to probabilistic lambda calculus, and it's another very nice possible line of work. Actually, you have there are plenty of possible generalization of this. It would be very nice to look at them and what they could bring, actually. Like Tsukada Sadeong proved that in a non-deterministic setting, this information about equivalence classes or typing derivation gives you the number, you can count with this, the number of reduction paths to normal forms. Okay, so I think that this can be generalized to probabilistic computation and using this general construction. I think it's possible, but you need some notion of enrichment somehow. I don't know. It's again, it's speculative, but it's interesting, very interesting possible direction.
Okay, so thank you.
Thank you, Francesco. And we have time for one last question, if there is any. Okay, fair enough. If we don't, we thank Federico one last time for his talk. Thank you very much, Federico. And I would say that for today we are done. And let me remind everyone that there will not be an online Ithaca Fest in December, but the event will be physical. So please do join physically in Genova. Some of us will be there. And so that's it. Thank you, everybody, for joining today. If you want to stay around,